Calculate the regulation of a transformer in which the ohmic loss is 1% of the output and reactance drop 5% of the voltage when the power factor is 0.80 lagging. So let's proceed to the solution. The problem states that when 1% of the output is ohmic loss, then the per unit resistance of the transformer E sub R equals to 0.01, and when 5% of the voltage is reactance drop, then the per unit reactance of the transformer E sub x equals to 0.05. So to solve for the regulation using the per unit value, we have E sub r cosine theta plus E sub x sine theta, where cosine theta is equals to 0.80, then sine theta is equals to sine times cosine raised to negative 1, 0.80 equals to 0.60. Now, substituting all the acquired value, we have the percent regulation equals 0.01 times 0.80 plus 0.05 times 0.0. This is 0.60 equals to 0.038 or 3.8%. So that's the regulation of the transformer. The primary resistance of a transformer is 0.10 ohms and its leakage reactance is 0.80 ohms. When the applied voltage is 1000 volts, the primary current of 50 ampere at a lagging power factor of 0.60. What is induced EMF in the primary? So now let's proceed to the solution. To solve for the induced EMF, we have the formula of E1 equals to V1 minus I1 times Z1, where V1 is equals to 1000, I1 is equals to 50 ampere, and the angle of cosine raised to negative 1, 0.60 equals to 53.13. Z1 equals to 0.10 plus 0.80 or 0.806, angle of 82.87. Then, substituting all the acquired values to the formula E1 equals to V1 minus I1 times Z1. So now we have E1 is equals to 1000 minus 50, angle of negative 53.13 times 0.806, angle of 82.87, where I1 times Z1 is equals to 40.4, angle of 29.44. Transforming this to polar form, we have the value of 35.18 plus J 19.86. So we can now directly solve for E1, that is equals to 1000 minus 35.18 plus J 19.86. That is equals to 964.8 minus 19.86. We can have the value of 965 angle of negative 1.18 degrees volts. So that's the induced EMF in the primary. If the EMF in the stator of an 8-pole induction motor has a frequency of 50 Hz and that in the rotor is 1.5 Hz, at what speed is the motor running? So let's proceed to the solution. To solve for the speed of the motor, we have the formula. So we have the formula of Nm equals to Ns times 1 minus slip, where Ns is equals to 120 times F all over P. That is 120 times the frequency of 50 Hz all over the 8-pole. That is equals to 750 RPM. So the slip of the motor is the ratio of the frequency 2 all over frequency 1. So where frequency 2 is 1.5 and frequency 1 is 50, that would be equal to 0.03. Then we have the formula of Nm equals Ns times 1 minus slip. So substituting all the acquired value, we have 750 times 1 minus 0.03. That would be equal to 727.5 RPM. So that's the answer for the speed of the motor. A 12-pole 3-phase alternator driven at 600 RPM supplies power to an 8-pole 3-phase induction motor. If the slip of the motor at full load is 3%, the full load speed of the motor in RPM is. Now let's proceed to the solution. To solve for the motor speed, we have the formula of Nm equals Ns multiplied by 1 minus a slip, where the supply frequency Fs is equals to P and all over 120. The value of P is 12 and N is 600 all over 120. We have 600 Hertz. Then the slip speed is equals to 120 times frequency all over P equals 120 times 60 Hz all over 8. That would be equals to 900 RPM. So now the formula Nm equals Ns times 1 minus slip. Substitute all the acquired value. We have 900 times 1 minus 0.03. That would be equals to 873 RPM. So that's the full load speed of the motor in RPM. A 15 horsepower, 230 volt single-phase synchronous motor is taking a current of 50 ampere at a power factor of 0.85 leading. Effective armature resistance is 0.20 ohms. If this motor drives a mechanical load of 12 horsepower, determine its rotational losses. So we have here the following given. Since the power of the motor is given with a value of 12 horsepower, converting it to watts, we have 12 times 746 equals to 8,952. Then the voltage per phase is equals to 230 volts. The current of 50 ampere. So we have also the power factor of 0.85. Then the armature resistance is also given with 0.20 ohms. So we are required to solve for the rotational losses or the P stray. Proceed to the solution. So we have your formula of Pm equals to P stator minus open parenthesis P copper plus the P stray close parenthesis, where the P stator is equals to Vp Ip cosine theta, that is equals to 230 times 50 times 0.85, that is equals to 9,775, where the copper loss is equals to Ip squared times the resistance armature equals to 50 squared times 0.20, that is equals to 500. Since we have acquired some of the values, so now let's substitute it to the formula. 8,952 equals to the P stator of 9,775 minus the copper loss 500 plus the P stray. So now we have the value of P stray equals to 323 watts. So that's the rotational losses of the synchronous motor. A 2,300 volts 3-phase Y-connected synchronous motor has a synchronous impedance of 0.2 plus J 2.2 ohms per phase. It is taking from the line current of 200 ampere at 0.5 leading power factor. Determine the induced EMF between the lines. Let's proceed to the solution. So we are required to solve for the induced EMF between the lines, or EL. So to solve for EL, we have EL is equals to E times square root of 3, where E is equals to V minus the voltage drop of current times the synchronous impedance, where V is equals to 2,300 over square root of 3, that is equals to 1,327.8. And the current of 200 at the angle of cosine raised to negative 1 0.50 equals to 60 degrees. Then the synchronous impedance of 0.2 plus J 2.2, transforming it to polar form of 2.2 to 1, angle of 84.8. Substituting all the given values to the formula, we have 1,328 minus 200 with the angle of 60 times 2.21, angle of 84.8. So we have the voltage drop of 442, angle of 144.8. So transforming this to rectangular form, we have negative 361.178 plus J 254.8. So simplify, we have 1,328 minus open minus 361.178 plus J 254.8 close parenthesis. So now we have the value of 1689 minus J 254.8, or we have the polar form of 1708 angle of 8.58. So therefore the EL is equals to 1708 times the square root of 3, that would be equals to 2958.8 volts between the lines. So that's the induced EMF between the lines.